old-fashioned. Yes, okay. So, yes, as Jim said, the question today is whether or not you can get rid of all of that nasty dark matter stuff by messing around with Einstein, with general relativity. So, there's, as you know, well, we'll just skip to the parts you know. Here's the standard cosmology. It works very, very well in terms of fitting the data, which is a good thing to do. You start with general relativity, Einstein's theory of gravity. You imagine that on very, very large scales, the universe is homogeneous and isotropic, so you know which metric to look at. Then you put ingredients in it, and this pie chart representing the ingredients is one of the most fantastic achievements in all of human history. It is in the 1990s, I like to say, will go down as the decade in human history in which we figured out what the universe is made of, which only happens once in human history. So my talk will be about, did we make a mistake? And the answer will probably be no. We really didn't make a mistake, at least not as far as this is concerned. So here we are. We're in the little wedge. 5% of the universe is ordinary matter, by which we mean every particle ever discovered in any experiment ever done here on Earth, ever. The entire standard model of particle physics only constitutes about 4 or 5% of the energy density of the universe. 25% of it is dark matter, this slice of the pie, and what we'll be talking about today is whether or not we can do better than that. 70% is dark energy, and it's that slice of the pie. If you want to know whether or not we can do away with dark energy by modifying gravity, you should go to my talk at 2 o'clock today. But that require a violation of general relativity to go backwards in time, so you probably won't be able to do that. There's some other stuff in the universe. There are neutrinos. There's radiation, you may have noticed. Many people make a living studying these things. And then you're not perfectly homogeneous and isotropic. There are adiabatic fluctuations on every scale of approximately the same amplitude of about 1 part in 10 to the 5. So it's an extremely impressive achievement that I can put on one slide, double-spaced, everything you need to understand how the universe operates on very large scales. But we are still not necessarily perfectly sanguine about the situation, mostly because of this pie chart. There are issues that this little pie chart gives us, among which is it's not as pretty as maybe we would like. I mean, it's kind of pretty, but it could be better in the sense that there are things we don't understand, like that part, and that part. We don't understand why, in this part, there is more matter in the universe than antimatter. We have ideas that would make that be the case. We don't know which of them, if any, is right. We don't understand what the dark matter is, which particle it is. We have reason to believe it's a particle. But we don't know which one it is. We have different theories, and one of them might be right, or none of them may be right. We don't know what the dark energy is. We have theories there that are not even as good as the dark matter theories. So making this inventory from a taking the list of ingredients, turning it into an actual recipe for the universe, is it this set of things? Why isn't it something else? Is the question that we need to do over the next 10 or so years. And the first thing to check is maybe we're being fooled by this whole picture. 95% of the universe in this picture is something we don't really understand very well. So the dark sector, the part that is both the dark matter and the dark energy, 95% of the energy density of the universe, is stuff that is a surprise to us. What we know about the dark matter, which you observe by looking at the dynamics of clusters of galaxies, or perhaps gravitational lensing. I'm sure everyone here has seen this picture before. The dark matter must be cold. If it were not cold, if it were warm or hot, if it were moving rapidly compared to the speed of light, it wouldn't have the time to settle into small-scale things like galaxies and clusters of galaxies, and you would see no structure on smaller scales. It is collisionless. If you look at the dynamics of a single galaxy, you notice that all the baryons and all the bright matter have cooled and settled down to the bottom of the potential well, whereas the dark matter remains big and puffy. That's because the ordinary matter can collide and radiate and cool off. The dark matter presumably cannot. Maybe it collides a little bit, but not that much. Then we have the dark energy, which is more mysterious, but we know a little bit about it. It's not true that we know nothing. It makes the universe accelerate. What that means is it is persistent. It does not go away very rapidly as the universe expands. The simplest possibility is that it's completely constant as the universe expands in terms of an energy density, 10 to the minus 8 ergs per cubic centimeter. Remaining constant, that would make the universe accelerate, but it could also be changing just a little bit. We also know that it's smooth, unlike the dark matter, which is very lumpy. The dark energy is smooth, otherwise it would be affecting the local dynamics of galaxies and clusters, which apparently does not. So we know something about these things, but we don't know what their fundamental nature is. We notice then, some irascible old skeptic says, look, you've only been tricked into thinking that there exists dark matter and dark energy, not because you've detected them directly, you've never felt them, you've never done an experiment where you made a dark matter particle or a dark energy field. You've inferred that they exist because of gravity. So you better be absolutely sure that gravity is doing what you think it is doing. What you think it is doing was figured out by Professor Einstein. It's important occasionally when you give talks to show pictures of Einstein looking young and well-dressed and haircut and when he was actually coming up with these great ideas that we give him credit for. Later, he sort of let himself go a little bit, but in 1912, when he was thinking about gravity, he was a nattily dressed young guy. Dark hair. Almost immediately after inventing general relativity is when he went gray. I don't know what the causal relationship is there. Okay. So in 1912, what he was doing was thinking about thought experiments. He said, look, let's say you have a box, and inside the box is a physicist who can't look at the outside world. Okay? But they're able to do experiments in the box. And they're thinking about gravity, they want to do gravitational experiments, so they take different objects and they drop them. This physicist seems to be dropping some big talismanic pagan symbol. I don't know exactly what it is. But you drop it, and you see what happens. And what Einstein says was that there's no experiment you can do in that tiny little box in a short amount of time that would be able to distinguish sitting at rest on some heavy body giving rise to a gravitational field versus accelerating at a constant rate in the middle of nothing where there's no gravitational field around at all. There is no experiment you can do that would distinguish between a strong gravitational field and empty space in an accelerating reference frame as long as you are confined to a small region of space and time. This is called the principle of equivalence, and when Einstein was faced with this, when you and I would be faced with this, we would say, that's kind of cool. You can't tell the difference between acceleration and gravity. Einstein, because he's Einstein, says that means that space-time must be curved. So there's an important difference here that everyone tells you this. You see this many, many times, and it took me years to figure out what is the connection. How did Einstein go from there to there? And the point is that this little thought experiment, which seems almost trivial when you say it, wouldn't work for any other force of nature besides gravity. If you ask exactly the same set of questions, but for electromagnetism, you would get a different answer. Put someone in a box, say, do experiments in electromagnetism, detect the existence of an electric field. And they would say, okay, drop an electron and a proton, and they would go in different directions in an electric field. The point of this experiment is that there isn't anything that goes in different directions under the influence of a gravitational field. Everything reacts in precisely the same way. And what Einstein's thought process was look, if everything reacts in precisely the same way, that's the same as nothing acting at all, as nothing happening. So we can think of general relativity not as a force propagating through space and time, but as a feature of space-time itself. And he thought a little bit further about what feature it would be, and he realized it could be the curvature of space-time. If we attributed to space and time a geometry, it could be bent, then you could have the sun in there influencing the geometry, and you could have the Earth. The Earth is just doing its best to move on a straight line. But there aren't any straight lines because space and time are curved, and the Earth ends up going around almost in an ellipse around the sun, and you have general relativity. So even though I know you guys are experts, I'll attach some equations to this. If you put coordinates on space-time, t, x, y, z, give them a Greek index mu and call them x0, x1, x2, x3, then the main thing, the thing you're dealing with when you're dealing with general relativity is the metric tensor. The metric tensor is this 4x4 matrix g mu nu that you sum over mu and nu with the infinitesimal elements of a distance here to get the line element, ds squared. So what g mu nu is telling you is a 4x4 symmetric matrix that is telling you how Pythagoras' theorem works in a small region of the universe, in a curved space-time, potentially in any coordinate system whatsoever. All of the information about how space and time are curved are just encoded in the value of the metric tensor, this 4x4 symmetric matrix. So what Einstein says was that the metric obeys an equation. It obeys Einstein's equation, which is relating Einstein's tensor to the stuff in the universe. And here's that relationship. You take the metric tensor and you construct from it a scalar, a function of space and time, which is just a number. And then you say, how can I use that to make an equation for what the metric does? And since you're a highly trained physicist, you say, I make an action. I make something which I will vary with respect to the dynamical variables to get equations of motion. If you vary the action and set the result equal to 0, you get the equations of motion. So what is the simplest possible action you can write? General relativity is a field theory, just like electromagnetism, Maxwell's equations is a field theory, or the Standard Model is a field theory. So what that means is that the action is going to be an integral over space and time of some function. And you ask yourself, what function could it be? It's going to be the curvature scale. This is the simplest thing you could write down. So you write that down, you add an action for matter, you differentiate the right-hand side with respect to the metric, and you get some equations. You get this equation known as Einstein's equation, which relates g mu nu with a capital G to T mu nu. G mu nu is the Einstein tensor, which is a certain way of characterizing how space and time are curved. T mu nu, the variation of the matter action with respect to the metric, is the energy momentum tensor, telling you how much stuff you have and what is the pressure of that stuff and what is the energy density of that stuff. So there's a differential equation for the metric telling you how curvature of space-time responds to stuff in the universe. So what we want to do is ask, can you do better? Or at least, can you do different? Can you think different? As Steve Jobs tells us to do. And you think, well, I would have to change this equation somehow. I have to either change the metric or change what it does or add new stuff. So you should think about how you can invent different theories of gravity. The main lesson of the talk, I think, that I'm trying to give is that is not whether general relativity works or not, but ultimately we'll figure out that it works. The thing that I most want you to come away with is some feeling for the constraints that you face when you try to modify gravity. So people who say, you've inferred dark matter, dark energy just by inventing something to fit the equations when the equations are general relativity, what if you had a different theory? You have this vague feeling that anything could happen, right? If you have a different theory than general relativity, who knows what could happen? You could fit anything. And that's not quite right. There are, in fact, constraints. You can't just invent all sorts of different theories. There are rules to obey, and the feeling for what those rules are is what I want to try to get across. So you're supposed to be asking questions at any time, right? Questions yet? No? Any minute there will be. So you want to invent a different field theory. General relativity is a field theory. Field theories work pretty well. You want to invent a different field theory. What would that mean? There are ingredients you need to include. You need to have some degrees of freedom. So you have some substance, whether it be space-time itself or the electromagnetic field or some crystal or some fluid or anything like that, and it has certain vibrational modes that are freely excitable in the absence of any source. Those are called degrees of freedom, whether it's condensed matter physics or astrophysics or field theory. They're classified by how many you have and what their spin is, as well as how they propagate. What happens to a freely propagating mode as it goes through empty space? Is it massless? Is it moving at the speed of light? If it is, it will give rise to a Coulomb potential. Electromagnetism does that. Gravity does that. If it's massive, then it takes more effort for it to extend out into space, and you get a Yukawa potential that cuts off exponentially. So massive degrees of freedom give rise to short-range forces, like the weak nuclear force. Massless degrees of freedom give rise to long-range forces. Finally, you'll want to tell me how it interacts with itself and with other stuff. How do these new degrees of freedom couple to other fields and to each other? So you're inventing a new theory means telling me this list of things. For example, you have general relativity. What would general relativity look like in this language? Well, the degrees of freedom are a graviton. The graviton is spin 2, which you may have heard. It is massless. It moves at the speed of light. And the thing it interacts with is the energy momentum tensor. So this sounds like I've quantized gravity. I'm talking about the graviton here. But all of these are perfectly classical statements. They're statements about what the freely propagating small perturbations look like in this particular classical field theory. So it's really talking about gravitational waves. How do you classify gravitational radiation? And you know what the answer is. You've seen these pictures where if you have a ring of test particles floating in space and a gravitational wave goes by, you have a massless gravitational wave, so it's going by at the speed of light, and it has two polarizations. Massless fields tend to have two polarizations. The photon is massless and has two polarizations. The photon, the two polarizations say if you have a charge and a photon goes by, it either vibrates it up and down or it vibrates it left and right. Those are the two orthogonal polarizations of a massless spin 1 particle. For a spin 2 particle, you have a ring of test particles, and either they get distorted up into an ellipse and then into a flat ellipse, and they go plus and minus like that. So they go in a plus sign, I should say. Or at 45 degrees to that, they get distorted into a cross or an X pattern. These are the two different independent polarization states of gravitational waves, corresponding to the two different polarizations of a massless spin 2 particle. If you had a spin 0 graviton, what would that do? What would happen if you added to general relativity something that was exactly like a graviton, that was massless, coupled to the energy momentum tensor, but was spin 0 instead of spin 2? The answer is it would take that ring of test particles and it would expand it and then contract it, and expand it and contract it. It would be a breathing mode, and it would be invariant under rotations, and that's what implies that it has to be spin 0. So that doesn't happen in general relativity. General relativity does not have any freely propagating modes that would make something increase in volume and decrease in volume. It's an interesting fact that everyone should know, and no one ever gets told. The other interesting fact is that when you look at these pictures, you go, you know what that reminds me of? That reminds me of what happens if you had a loop of string and you let it vibrate. It could vibrate like this, back and forth, or it could get bigger and smaller. You would say, I bet if I took a little loop of string and quantized it, I could invent a good theory of gravity. You would be right. People have already noticed this. It is not a coincidence that these little pictures that are the answer to the question, what would a loop of test particles do when a gravitational wave passed by, are also the same pictures you would draw if you asked, what are the fundamental vibrational modes of a little loop of string? The actual vibrating loop of strings are why string theory really does necessarily predict the existence of gravity. In fact, it predicts gravity with an extra spin 0 particle that you don't get in general relativity. And it's work to take that spin 0 particle and make it invisible so that we haven't noticed it yet. So let's talk a little bit about what life would be like with an extra spin 0 gravitational field. So you can imagine theories called scalar tensor gravity. Tensor refers to the tensor field we already have, the metric tensor, that tells you what you know and love about the geometry of space-time. So you add a new field, a scalar field, something which is spin 0. What does it do? Well, you could write down an action, but we'll skip right to the equations. Here are Einstein's equations relating the Einstein tensor to energy and momentum. In the presence of a scalar field, you get the Einstein tensor still related to the energy momentum, but there's a new contribution to the energy momentum tensor from the scalar field phi, and the strength of gravity now depends on the value of phi. So what you thought of as Newton's constant is now Newton's variable, something that changes from place to place throughout space. This is why you have to be careful. This would be in violation of all sorts of experiments if phi were changing noticeably from place to place in our real universe. So phi is a new degree of freedom that didn't exist in general relativity. It's tightly constrained by actual experimental tests. Here's a picture of an experimental test. This is the Cassini mission, which we told NASA was to take pictures of Saturn. It was a satellite that we launched from Earth to take pictures of Saturn. But really, what it was really doing was testing general relativity in the solar system. And it was doing that by beaming signals past the sun that we would record here. And Erwin Shapiro showed a long time ago that as those signals go past the sun, they slow down. There's a time delay. It's always moving at the speed of light, but space and time are curves. There's a time delay, and the amount of time delay that you get that you can measure very precisely because you built this thing so you know where it is. You can figure out whether or not the shape of space-time in the solar system is what general relativity says it should be or not. The answer is yes, it is in fact what general relativity says it should be. You can parameterize deviations from what general relativity says by the Bronsticki parameter omega. Omega is constrained by the Cassini mission to be greater than 40,000. You reach general relativity in a limit where omega goes to infinity. So compared to order unity, 40,000 is practically infinity, so you're very close to general relativity here in the solar system. If there were a freely propagating scalar field, omega would typically be of order unity, unless you worked hard to find it. So you can do things like this. You can test general relativity, both in cosmology and in elsewhere. So here are the kinds of tests that are relevant to gravity when we talk about the entire standard cosmological model. You have general relativity plus dark matter plus dark energy. and you have a whole bunch of phenomena that depend on these and can be used to test them. The solar system and the binary pulsar are sort of localized things that let you look at the gravitational field in a local region due to some small objects, and they're testing general relativity to great precision in very different regimes. Big Bang nucleosynthesis tests general relativity because when the universe is a temperature of 1 MeV, when it's about a minute old, it's a nuclear reactor. It's turning protons and neutrons into helium and lithium and deuterium. And what it wants to do, what those protons and neutrons want to do, is to minimize the curve of binding energy, or maximize it, whichever way it goes. They want to be iron, right? The lowest energy state of protons and neutrons is in iron nuclei. Why didn't the early universe turn all of its protons and neutrons into iron nuclei? The answer is because it was expanding. So they were trying to get together to form nuclei, but it was expanding so fast they couldn't get there. And pretty soon they were too dilute to have any more nucleosynthesis. So the amount of the different elements you get depends very sensitively on how fast the universe was expanding back then. And that is a test of general relativity. But dark matter and dark energy have no effect on that because they were both very negligible way back when. It was a radiation-dominated universe. Things like lensing by clusters are a way to weigh the cluster, which involves general relativity, but depend on the dark matter. So the dynamics of a cluster all by itself doesn't test general relativity because it lets you weigh the cluster. There's no way to check that you got the right mass. If you weigh the cluster by looking at the dynamics and then also weigh it by looking at lensing, then you're getting the mass two different ways, and that is a test of both the dark matter exists and of general relativity. The power spectrum of fluctuations depends on all of these things, and we'll talk a little bit about that. Likewise, predictions for the CMB depend on all those things. The supernovae tests really only depend on general relativity and dark energy. They depend on the total mass density, but they don't really care whether it's dark matter or ordinary matter. So, with that as background, so are there any questions about how you might try to change general relativity? What you might do to modify gravity? I'm the one who's given 2 talks today. I don't know why you are all so tired. You're going to... So, Milgram was inspired by doing this. He said, we should modify gravity. This dark matter stuff just rubs me the wrong way. The best way, I think, to state what Milgram said was to notice that he pointed out a fact about what was known at the time about galaxies. That where you need dark matter in galaxies is not at the same radius away from the galaxy every time. For different sized galaxies, the dark matter kicks in at different points. So here's a spiral galaxy, here's the distance, here's a rotation curve. So if the ordinary matter that we saw was all there was, the rotation curve would go up steeply when you're near the center because there's more and more matter that you're including inside your radius. But then once the matter started falling off, the velocity should also fall off, a la Kepler, but it doesn't. So there's some point here where you need to start including matter that you don't explicitly see, which we call the dark matter. What Milgram pointed out is that the place you need to start doing that, if you evaluated the radius, it would be different for different galaxies, but if you evaluated the acceleration due to gravity, it's very close to the same for every galaxy that you see. The acceleration due to gravity, in the Newtonian sense, at the point where dark matter kicks in is about 10 to the minus 8 centimeters per second squared. It's an interesting fact. One way or the other, that is an interesting fact. Another interesting fact is that it is approximately the Hubble constant in units where c equals 1. It's just a fact. You can't blame me, I'm just telling you the fact. Milgram, though, couldn't leave well enough alone. He said maybe this means something, this fact. Maybe it means that gravity is not right, that general relativity is not right. In fact, that Isaac Newton was not right. Forget about Einstein. We're talking Newton not being right here. So he proposed a phenomenological rule called MOND, modification of Newtonian dynamics, where gravity falls off more slowly when it's very, very small. So the force due to gravity, when the acceleration is greater than a0, is just what Newton said, 1 over r squared. But when it was less than a0, it was 1 over r. It's falling off more slowly. Actually, this is not at all what Milgram said. What he modified was not 1 over r squared. He modified F equals ma, but it turns out to be equivalent to this for our purposes. The next surprising thing is this idea works really, really well for a whole bunch of galaxies. Here's one cherry-picked example where it works quite well. This curve is the actual rotation curve measured for some galaxy or the other. I don't have it written down here. And here's the prediction for MOND. Sorry, the points are the actual data. The line is the prediction for MOND. Does pretty well. There's even a little bump. Gets that right. So there's a whole bunch of galaxies you can show like this. MOND generally does a quite good job. It gets the Tully-Fisher relation popping out rather than as some mysterious phenomenological thing that you notice. There are no problems on the centers of galaxies with cuspiness of cores or anything like that because there's no dark matter. It's just ordinary matter. And it even works well for low surface brightness galaxies where there's not a lot of dark matter, and it hadn't been measured in 1984 when Milgram did the inventing of MOND. So it has something going for it simply as a phenomenological description of how galaxies actually work. So you can ask, is it just a coincidence? Does ordinary general relativity plus dark matter combine under various dynamical circumstances to reproduce all of these things? Or is it really that force law is a fundamental law of nature? Well, no, that force law is not a fundamental law of nature. Here's why. It's been known for a while that MOND does not work in clusters of galaxies. So it works really well for individual galaxies, but in clusters of galaxies, you can just check, and it is often the case that the acceleration that these galaxies feel is below the value where MOND should be kicking in, where it should be relevant. But you don't actually get the right answer. The sort of virial mass that you would get for these clusters of galaxies is not correctly predicted by MOND if you just add up all the stuff you see inside the cluster. It's generally off by a factor of about 5. To be generous, we'll say it's off by a factor of somewhere between 2 and 10, because you can argue about how much baryonic matter are in these clusters. Even the MOND partisans have given up as far as clusters of galaxies are concerned. If you ask people who really like MOND how they can explain clusters of galaxies, they will say, well, we need dark matter. They won't say it in that short a phrase, but they will say it over the course of many paragraphs of text. And what they're saying is the following. They're saying, what if neutrinos were massive? Neutrinos we know have masses. We've measured that they actually have difference in masses from one neutrino to another. That couldn't be the case if the masses of all of them were 0. So some neutrinos have mass. They differ in mass by maybe 10 to the minus 3 electron volts for the lightest neutrinos. So what if neutrinos had masses of something like 2 electron volts? It turns out that you run through the numbers, that you get a substantial contribution to the total energy density of the universe, where omega neutrino is something like 0.17, and that's enough dark matter to fit clusters of galaxies in the context of MOND. And you say, but I thought the whole point was to get rid of the dark matter. And they say, well, but the neutrinos are at least in the standard model of particle physics. Before, you had to have non-standard model particle physics candidates for the dark matter. The point is that neutrinos all by themselves are not cold dark matter. They're warm or hot dark matter. And hot dark matter or warm dark matter doesn't fit the data all by itself because you can't make small galaxies with anything like the number densities we see today. Neutrinos tend to go out of small overdense regions just because they're freely streaming because they're light. The combination of neutrinos in clusters of galaxies where they can stick and MOND on small scales, so the argument goes, can fit the data. That turns out actually to be right.
So because the neutrinos are hot, they fill the Tully-Fisher relationship and so forth?
No, MOND does that. The point is the neutrinos don't bother the individual galaxies, they only bother the clusters. So that was an empirical problem. You can decide for yourself whether or not the fact that you need neutrinos in clusters of galaxies convinces you shouldn't worry about MOND anymore or not. I don't know if that sentence really ended where it was supposed to, but you can decide for yourself. Meanwhile, there are theoretical problems with MOND. One problem is that it is modified Newtonian dynamics, and we know that even good old non-modified Newtonian dynamics is not right. We know that general relativity is closer to right. Not only is this a new force law for gravity given rise to things like the precession of the orbit of Mercury, it's also a new way of thinking about space and time. So in Newtonian gravity, there is something called the acceleration due to gravity. In general relativity, there isn't any such thing as the acceleration due to gravity. Particles are moving on straight lines as well as they can. They're not being accelerated under what you used to think of as the acceleration due to gravity. Einstein had this little thought experiment where he showed that you can't measure the acceleration due to gravity. So if you try to naively take Milgram's idea that gravity changes when the acceleration dips below some value, you can't even ask that question or state that result using general relativistic language. So it's hard to know how to make a modification of Einsteinian dynamics that would somehow reproduce Mond. And if you don't have a relativistic formulation, there's a whole bunch of questions you can't ask. You can't ask what kind of gravitational waves do you get, so you can't reproduce the success of the binary pulsar. You can't ask about gravitational lensing, because photons sadly move at the speed of light, which is relativistic. So you can't check consistency with the masses of clusters. You can't do the expansion of the universe, so you can't check with nucleosynthesis or with the current Friedmann equation. You can't do the growth of structure as the universe is growing. So the point is that general relativity plus dark matter and dark energy has passed a lot of empirical tests. And even though Mond does very well at fitting individual galaxies, it's not being subjected to these same tests that general relativity has passed. So theorists tended to think that it was not, in any sense, a respectable competitor to general relativity. So let me talk a little bit about this particular thing, the idea of getting Mond and plugging into cosmology. The point is that the ordinary theory, general relativity plus dark matter and dark energy, fits very well. How much would it have to be an accident for a completely new theory to get exactly the same answers? Here is the power spectrum of large-scale structure. As a function of scale, from small scales to large scales, and out of density fluctuations in the universe today. The point is that we've measured the power spectrum of large-scale structure over a huge range of different scales, from the whole universe, using the cosmic microwave background, through clusters and through individual galaxies, down to relatively small lumps of stuff in the Lyman alpha forest. And even though, it begins to deviate just at the tail over there, the overall agreement over this huge range of fluctuation, amplitude, and scale is really, really impressive. If you start messing with your theory of gravity in random ways, you're not just going to, by accident, take this exact same amount to fit. It will require something going on, just by coincidence. Furthermore, I wanted to say that the fact that it fits is not just something a general relativity statement. It's very much reliant on the existence of dark matter. If you don't have dark matter, if you just have baryons in your universe, even if you have more baryons, the baryons tend to be coupled to the photons, and the photons don't want to clump on small scales. They want to move at the speed of light. So a just baryonic universe tends to wipe out this structure that you see. You notice that the value is larger on small scales than on large scales. Without dark matter, you would get something that went up and then went down again. That's not what the data actually do. Then you have the microwave background, and this is even better in terms of convincing yourself in a completely model-independent way that there must be something like dark matter. So here's the rough argument, which is worth going for. This is the amount of temperature anisotropy in the cosmic microwave background as a function of angular scale. And so this is large scales, these are small scales, and you get this nice curve with bumps and wiggles on it. And these bumps and wiggles are literally snapshots of acoustic oscillations in the primordial plasma caught at the moment of recombination 400,000 years after the Big Bang. So on smaller scales, what you have is overdense regions which were frozen when their physical size was larger than the Hubble radius in the early universe, and then began to evolve when the universe slowed down and their physical size became smaller than the growing Hubble radius. So when they began to evolve, an overdense region collapses, it heats up, and you get a peak. But then it has pressure because it just heated up, and it responds to the pressure by bouncing back and becoming an underdense region, and then you get another peak. And then it collapses again, and it's an acoustic wave. It's bouncing back and forth. So the largest peak right here is the size, corresponds to the size of an overdense region that had the chance to collapse and heat up, but not the chance to respond again. That is the largest amount of fluctuation you get. The ones that have bounced back and forth get damped, because even though the oscillations are bouncing back and forth, there are still relativistic particles that are doing their best to smooth everything out. So what you would expect a priori from an initially flat perturbation spectrum is a sequence of peaks, every one lower than the previous one, as they're damped on smaller and smaller scales. The thing is that the dark matter doesn't bounce. Initially, both the dark matter and the ordinary matter are overdense in the same place. They collapse under the force of gravity. They heat up. But then the dark matter just keeps collapsing. The ordinary matter heats up and bounces. So at the odd-numbered peaks, here, here, here. The dark matter and the ordinary matter are in phase and working together. The even-numbered peaks, there and there and there, they're out of phase and working against each other. The effect of dark matter is to boost that third peak, shrink that second peak. So instead of a uniform going down, there's a huge dip from the first to the second, and the second and third are almost at the same scale. That is the prediction of a model with dark matter in it. It is almost impossible to make that happen in the absence of dark matter. You can't get that kind of behavior with modified gravity. So, sadly, you can't compare MOND to general relativity or lambda CDM according to these standards until you invent a relativistic model, and here it is. Bekenstein invented a theory called TEVIS for tensor vector scalar gravity that was finally a relativistic way to do what MOND wanted to do. So he had a tensor field, the metric, which we know and love. He added a scalar field, which we anticipated. And he also added a vector field. And I will tell you why he had to add a vector field in just a second. So there's 2 points to TEVIS. One is that the metric that you feel when you drop things and they respond to gravity and so forth is not the metric that obeys the Einstein-like equations. The metric that obeys Einstein's equations is that G. The metric that you feel is G tilde, which is this complicated combination of things. That is one fact. And then I skipped the result here. The result is that not only do you get MOND right, but the claim of Bekenstein is that he went through the gravitational lensing calculation where you weigh a cluster of galaxies by calculating its virial mass and by looking at the lensing, and using MOND you would get the same answer using those 2 mechanisms just like you would for cold dark matter plus general relativity. This is the one part that I really should tell you about since the lensing program, but I'm not going to tell you about it because I don't know anything about it, but I'm going to believe him. The price that you pay is you violate Lorentz invariance. So he has a vector field, but this vector field points in some direction. It establishes a rest frame that you can measure your speed with respect to, and I'll talk about that more in a second. Why did it take so... Sorry?
Does that mean that if you had a rapidly moving galaxy, the lensing wouldn't work?
Basically, yes. Unless it dragged the vector field along with it in some interesting way, but basically, yes. You don't have any rapidly moving. There's not any galaxies moving at half the speed of light across the universe. So.
Well, high Z, the recession velocity is high. So
oh no, but that's just the expansion of space-time. You need to be moving with respect to this reference frame, which galaxies are not. Yeah.
And so does this do things like the perihelion section of Mercury?
The claim is everything works fine. Yes.
What about the strong field test, like the radiation from the binary pulsar?
I think that was not checked in the original papers. I don't know if anyone has subsequently checked it. I know from the experience of scalar tensor theories that it's often, the binary pulsar is sort of surprisingly not a good way to detect new degrees of freedom. But I'm not sure. I don't know what the... It would be interesting to know the answer, which I don't know. I know that the location of the Barry center, right, is somehow very tightly constrained, and if you have a vector field with respect to which you can measure the speed, that might be a good constraint, but I just don't know. I think it's ruled out, so I'm not going to bother to calculate that. So let me tell you. Yeah, but by something else. Now, you notice, so 2004, Bekenstein wrote down this theory. When did Milgram invent MOND? It was 1984. Why did it take Bekenstein so long, 20 years, to invent a relativistic version? Was it because, number one, he hadn't heard of MOND? No. He's best friends, actually, as it turns out, with Milgram. They work together all the time. Number two, maybe he's not that smart? No. He's very smart, Jacob Bekenstein, and he worked very hard on this. Why did it take him so long? Well, I don't know the answer, but here's the theory he came up with, and you can decide for yourself how long it would take you to come up with this theory. He said, okay, we'll start with general relativity. We'll add a vector field, a scalar field, and a Lagrange multiplier field. Will be important in a second. Here's the action. It's just general relativity. What's so hard about that? Plus a couple other terms. There's a term for the vector field, which does the following thing. Here's the Lagrangian for U. F mu nu is just what it would be for electromagnetism. So electromagnetism also has a vector field, the vector potential A mu, and the kinetic energy for that vector field is F mu nu, E squared minus B squared. Okay, so you can calculate that. And there's some constant. Then there's a new term. Oh, actually, lambda is also another Lagrange multiplier. So this new term says, take the norm of the vector field, g mu nu, u mu u nu, which is going to be a negative number, add it to 1, and set the result equal to 0. The equation of motion for lambda sets the norm of the vector field to be precisely 1, minus 1, all the time. So the length of the vector field never changes. It's fixed. That is exactly the opposite of electromagnetism, where, of course, the vector potential can be 0 and fluctuate up and down, and we see that as like light. Okay, so it's a fixed norm vector field. Here's the Lagrangian for phi. What would you expect the Lagrangian for phi to be? It would be d mu phi times g mu nu. So you see that there. But here you've added something interesting, which is another coupling of phi to the vector field. Why do you have to do that? The reason you have to do that is because otherwise you don't know what the acceleration due to gravity is. The whole point is that general relativity doesn't know what an acceleration is. There's no reference frame with respect to which you can measure it. This vector field gives you a frame. It violates Lorentz invariance. It picks out a frame. And the coupling of that vector field to the scalar field knows about the acceleration due to gravity. That's the extent to which it's more Newtonian than Einsteinian, although it's still perfectly, the dynamics are perfectly invariant under coordinate transformations, etc. The real trick of this is this eta business. So here's eta. It has a potential. That's what you would guess. If you were writing down potentials, you would guess it would be 4 plus 2 eta squared minus 4 eta cubed plus eta to the fourth plus 2 the log squared of eta minus 1. And what does eta do? You notice it's innocently sitting there multiplying this, and then it has this potential. There's no derivatives of eta anywhere. The equation of motion for eta is just an algebraic function. It sets dv d eta equal to this function of phi. So that's an equation of motion you can solve, and what you get is eta equals some incredibly ugly function of phi, and you plug that back in. So really, these two lines together are just telling you that the Lagrangian for phi, the kinetic energy for phi, is not the simple thing you guessed. It's some incredibly ugly function of d mu phi coupled to the vector potential. When you see functions like this, when you see there's a plus 2 there and a minus 4 there and a plus 1 there, you know that whoever came up with this function was working really hard, and if this were minus 3, it wouldn't have worked. Right? Otherwise, you wouldn't have had that term there. You wouldn't stumble on it by accident. You had to work hard. So before talking a little bit about the explicit results of this theory, let me sort of warm you up or tenderize you by talking about what it means to have a vector field.
Sean,
Yeah.
before you do that, so it's just the spatial derivatives of phi which enter, because g minus uu is just the spatial.
The coupling to u, yes, that's right.
Okay, so one question which came up earlier this week is about acausal propagation.
Mm-hmm.
Get elliptic equations for
Right.
Are you going to talk about that?
I'm not going to talk about that. It's something one should talk about.
Is that true?
I'm just going to talk about data. So in other words, you want to know, in all of this, what one should do, is decompose all the different modes of these fields, all the different modes of the vector field and the scalar field, into small perturbations, look at the linearized equations, and ask whether there are ghosts and tachyons and things like that. I don't know the answer. It's something you certainly should be worrying about. It's not something you should toss off. Yeah, I mean, in other words, if there are ghosts or tachyons or acausal propagation, you don't need to compare this theory to the data. It's just wrong. It's just ruled out by the fact that, phi particles are not appearing in empty space right in front of us. So that should be done. I think it's okay. I remember being vaguely told that someone said it was okay, but I don't want to promise you. So let's talk about violating Lorentz invariance by having a vector field throughout space-time. The reason why I want to talk about this is because it was the subject of my first ever published paper, which I was sure was going to be the end of my career as a working theoretical physicist, because back in 1990, it was not cool to go around violating Lorentz invariance. These days, everybody does it, but we were there first. And it's really not so bad. I mean, it sounds bad violating the Lorentz invariance. Some things should be sacred and some things should be left alone. But you're very used in particle physics to having scalar fields have non-zero expectation values in empty space. That's how, in the standard model of particle physics, you get things like the mass of the electron, which we know and love. There's a scalar field that has a non-zero value in the vacuum. Once you allow that to happen, there's nothing in principle that would say you shouldn't have vector fields that have non-zero values in the vacuum. And if so, you would just have this is the lowest energy state of space, would have this vector field pointing in some direction, more or less constant across space. So it violates Lorentz invariance, which means there are performed framed effects once you start coupling this vector field to matter. It's turned into a whole little industry in atomic physics and particle physics to actually test Lorentz invariance by taking vector fields like this, writing down interactions between these fields and the fields in the standard model of particle physics, and putting constraints on how big they are. The nice thing is that you can put such good constraints on violations of Lorentz invariance that you're actually testing Planck scale physics if there's any violation of Lorentz invariance at all. Something that was actually not asked until very recently was what are the gravitational effects of these vector fields. So if you have some fields, they will have an energy momentum tensor, right? How do they affect the expansion of the universe, for example? So it depends on the Lagrangian that you write down, the action, the equations of motion for the vector field. Bekenstein has given us one such action. I just want to ask the question in the much, much simpler context. Forget about Lagrange multipliers and phi and all these scalar fields and Mond and so forth. Let's just put a vector field down there with the simplest possible action, give it a constant expectation value, and ask what it would do. Well, here's the answer. You would have Einstein's equation, so you just have an energy momentum tensor for ordinary matter plus an energy momentum tensor for the vector field in some configuration. Let the configuration be that the vector field is constant. It's not doing anything. Let the background be cosmology, so a homogeneous and isotropic universe expanding as a function of time. So you know where to point this vector. It's pointing orthogonally to all the space-like hypersurfaces. It turns out, just through a miracle, that when you calculate the energy momentum tensor of that vector field, it equals minus something times the Einstein tensor. The vector field isn't changing. There's no derivatives of the vector field in space or time, so the only thing that the energy momentum tensor can be a function of is the scale factor. It turns out to be the same function of the scale factor as the Einstein tensor is. So, what you really mean up here is that this guy is actually proportional to that guy. So you can move it over there, get 1 plus alpha times g mu nu, divide by 1 plus alpha, and get this. In other words, the effect of a constant norm vector field all by itself in a cosmological background is just to change the effective value of Newton's constant by some factor that depends on the length of the vector field and goes to 0. Alpha goes to 0 as the length of that vector also goes to 0. That's an interesting fact. All by itself, what it would mean is that the presence of the vector field is completely unobservable unless you thought you knew what Newton's constant was. Some of you might think you do know what Newton's constant is. How do you know it? You know it by doing experiments in the solar system. So you can go through the same exercise, calculating the energy momentum tensor of the vector field in the solar system, and you find that again, the vector field energy momentum tensor is proportional to the Einstein tensor, but with a different coefficient, beta, instead of alpha. And the coefficient has a different sign. It's positive here instead of negative here. So what that means is that if you measure Newton's constant in the solar system and measure it using the expansion of the universe, you would get two different answers. The way the effect goes is that it slows down the expansion rate of the universe, and you can use that to put a limit on the size of this vector field. It's not a very good limit. It's something like 1/10 of the Planck length, of the Planck mass, or something like that. But it does show you the kind of thing that a vector field does. It doesn't act as dark energy. It doesn't make the universe accelerate. All it does is renormalize the value of Newton's constant.
Does this mean that this kind of equality, this theory will automatically be consistent with the so-called preferred frame parameters of post-Newtonian expansion?
Not exactly, because this is sort of the 0th order thing that it does. If you want to, so this is a perturbation, this is the Newtonian limit, where everything is slowly moving compared to the speed of light. Not post-Newtonian, it's actually Newtonian. Once you go post-Newtonian, then the vector field is going to be moving. It's going to be changing its value from place to place. That's going to change things. So you can, in principle, if the Earth is moving through some background vector field, you could certainly imagine detecting preferred frame effects.
You know what that's
Yeah. Not these guys, sorry. These guys, Jacobson and Mattingly, have been looking at those kinds of things. They're putting different limits. So obviously you have a parameter space, and you put limits on the parameter space. It's not great, actually, the limits. Okay, so that's just to warm you up. You're all now tender and juicy, and we're going to do Tevis. So these guys, Scortis, Mota, Pereira, and Baim, wrote a great paper where they actually took that horrible action that Bekenstein wrote down and modified all of the codes you need to do perturbation theory and cosmology to do it in the presence of that theory. There are many papers written about cosmology in Tevis, but they almost all cheat. They almost all say, well, I can sort of see that this is going to happen, so I'll just make that happen in my code. Very few of them actually put the theory into CMB fast or whatever. These guys did it. And here's what they find. They find the Friedmann equation is basically unaltered. You really kind of, the presence of this vector field and the presence of this scalar field don't add substantial amounts to the energy density. They slightly change the time dependence of Newton's constant, but not in a noticeable way. Likewise, the scalar field doesn't add much to rho. The vector field does not add much to rho. The scalar field actually tracks, so if you give it initial conditions so that it's 1% of the energy density of the universe, it will stay 1% of the energy density of the universe, which is not detectable. So the expansion is basically normal, which means, among other things, that Tevis does not make the universe accelerate. If you want to fit the supernova data in the microwave background, in this theory you are going to need dark energy. It does not get rid of dark energy, it's trying to get rid of dark matter. So you put not only neutrinos and dark matter, you also put dark energy in there, but still, you fit the data, is the nice thing. Here is the power spectrum, and here are some data. Here is a scale from large scales to small scales. Here's the amount of power. And here's lambda CDM, doing a pretty good job of fitting the data. Here's what MOND would do without the dark matter. And it sort of does okay, but it's sort of systematically low. But as long as you put in both the dark energy and the neutrinos, it just goes smack through. It's really, really good.
And neutrinos are the same level you needed to fit clustered.
Yeah, that's right, 0.17. It's kind of surprising that it does so well, because we just said that small-scale power wants to be wiped out if you have neutrinos streaming out. But what happens is the scalar field, phi, freezes according to its initial perturbation that doesn't evolve very much. So it's sort of a leftover, almost like an amount of dark matter that is preserving the potential wells for the galaxies to be falling into. Even better, the CMB does pretty well. Here is 3 different curves. Lambda CDM is this dotted curve. Tevis with just the cosmological constant comes nowhere close if you don't include the neutrinos. It's just wildly ruled out. But if you include the neutrinos and the dark energy, here it is. For the second and first peak, it does a really good job of fitting the data. The difference is in the third peak, just like we predicted. Basically, those neutrinos are helping you with the second peak, but then they work the wrong way in the third peak. Lambda CDM predicts a noticeably higher third peak height than MOND would do. These data from WMAP and CBI don't really do a very good job of distinguishing, although I would certainly say that Lambda CDM is fitting better. There's subsequently been better data since the Scortis et al. Paper from Boomerang, and it's become even clearer that the third peak really is there, where Lambda CDM wants it to be, not where MOND wants it to be. But I don't know of any paper that has actually compared those two in a respectable way.
4,000, LO4000 from CBI. I mean, you should go further in the background.
Well, I wouldn't be surprised if they're close. I mean, I don't know if the thing that you really care about is not the amplitude, but the difference in amplitude between the odd-numbered peaks and the even-numbered peaks. I don't think that at LO4000 we're there yet. We're not measuring the 6th peak yet.
But you've got to choose the neutrino mass.
Yes. But once you know that and that, you've chosen the neutrino mass. You don't get to choose it again down there. That's right. And you choose it to be crazy. Oh yeah, then you're done. That's right. A prediction.
The standard expression, what we know before, omega nu in terms of mu is something like something like omega nu a squared is like m over 100.
Yeah, something like that, right.
So to get 0.17, you need something like a 17 eV neutrino, is that right? Or 9 eV neutrino?
Well, let's see. You need 3 2 eV neutrinos is the claim. So once you put H in there, something like that. I'm not going to get the factors of 2 right now. So this is what the paper says. So that's I don't know where. When I say 2, you shouldn't believe me. It's something like 2. When I say 2 electron volts is that it's not 10 to the minus 3 electron volts. That's the lesson. It's very far away from the natural value. Okay. So as far as cosmology is concerned, here's the lesson. You do pretty well. You do better than you had any right to do with Tevis when you try to fit the perturbation spectrum and the cosmic microwave background. But you don't do perfectly when it comes to the third peak. If you really knew exactly what the third peak was doing, you would know whether Mond was right or whether CDM was right. Let me also then talk about the bullet cluster, which I probably don't need. You probably heard talks, right? Does anyone not know what the bullet cluster is? Yeah. Okay. My only connection to the bullet cluster is that I was there for the press conference, but I can nevertheless tell you that there are certain things you might have heard about the bullet cluster that are not true. Here's the story. You had the cluster there. I'll just go through it very quickly. It's a cluster of galaxies. Look, another cluster of galaxies. And when you look for the X-rays, the X-ray gas, which is most of the baryonic matter in the clusters, is displaced from where the actual galaxies themselves are. That's because, the story goes, these two concentrations went through each other. The X-ray gas smacked into the X-ray gas from the other cluster, underwent a shock, and got stripped from the actual location of the galaxies themselves. The galaxies are just like test particles, they went right through. When you look for the location of the matter, when you look for the location of the gravitational field in the bullet cluster, by doing lensing, which is what you guys are good at, you find that here's where the gravitational field is. The gravitational field is concentrated around where the galaxies are in these two separate concentrations, not where the ordinary matter was. Matter, gravity, matter, gravity. So the bullet cluster is teaching you in a very, very explicit way that you see an example where the gravity is not pointing toward the matter. It's not because the strength of gravity is falling off in a different way, which is the prediction of Mond or almost anyone's theory of modified gravity, is that the direction of the gravitational force is somewhere else. The fact that this blue is concentrated there means that right there, the light of the distant galaxy is being deflected toward here, which if all the matter is there, wouldn't happen, even if gravity were being modified. So, the lesson of the bullet cluster is that dark matter exists. There's gravity pointing in a direction where there isn't enough ordinary matter to explain it, to source it. No matter what the strength of gravity is, the direction is pointing somewhere else. You can't explain this just by modifying gravity in any plausible way. No one has a theory that says that the gravitational field points in the direction where the matter would have been if it hadn't run into some other matter somewhere else. No one has such a theory, and don't let them have such a theory. We know from BBN and the microwave background that the gravity that we see in the bullet cluster formed by dark matter is not formed by baryonic dark matter because there's upper limits on that. So this is really non-baryonic dark matter. Now you might say, people have said, we didn't learn anything from this. People have said this because I already told you just from clusters of galaxies and from the CMB that Mond needs omega neutrino to be 0.17. The point is that I'm not talking here about Mond, I'm talking here about modified gravity in a perfectly general way. Mond might not be right, but gravity could be modified. That is a possibility that we should be open to. What the bullet cluster is telling you is that you can't, just by modifying gravity in any plausible way, explain this data without also having dark matter. Now, there are some people who claim to do that. They say, well, I have a modified theory of gravity, and I do a lot of equations, and I plug it into the computer, and I fit the bullet cluster. They're lying, not about the fact that they fit the data. They might very well fit the data. That's fine. In fact, it's interesting to fit the data. I'm a big fan of fitting the data. But secretly, they have dark matter. That's what I want you to believe. Because, or maybe not so secretly, the point is that I already told you that the way to invent a new theory of gravity is to add new degrees of freedom to your theory. That's what you need to do. Add some more fields. Bekenstein added a scalar field and also a vector field. Other people have added other theories with other amounts of degrees of freedom. Now, these degrees of freedom have their own actions, they have their own Lagrangians, they can propagate freely through space all by themselves. The way to explain this data in such a theory is for the extra degrees of freedom that you have in your theory to be sourcing the Einstein tensor there and there. So you have freely propagating excitations of a field whose energy momentum tensor is sourcing the curvature of spacetime. What we call that is dark matter. It might be part of a theory that you invented as an attempt to modify gravity, but it's dark matter. It's degrees of freedom with an energy momentum tensor that are curving spacetime. So, regardless of how you try, the lesson of the bullet cluster is that you need new degrees of freedom that are propagating, not just being sourced by ordinary matter, but freely propagating in a different place. And I'm all in favor of looking at new theories doing different things. It might very well be there's dark matter and modified gravity. That is very plausible, and you could try to look at that. But I think you need dark matter. Dark matter really exists in one form or another.
So, in the particular case of Travis, say, do we learn anything new from the bullet cluster? I mean, you fit, when you put in enough neutrinos with the bullet cluster, is it the same number as you would have used anyway?
I don't know. Do you know?
The problem is you can only fit the weak lensing data, but
Not the strong lensing data. Okay. I mean, yeah, this is where real astrophysics becomes necessary. Now you're into the nitty-gritty, which is great. I'm all about the nitty-gritty, but you need some dark matter, which is my thing, yeah. So, I mean, I'm trying to push it both ways here. Some people say that you've ruled out MOND. That's not true. You have not ruled out MOND if you have enough dark matter along with your MOND to fit the other data. Other people say, I can fit it without dark matter. That's not true either. You need some degrees of freedom that are propagating there in empty space.
What about your third peak?
My third peak also needs some degrees of freedom. They're not coupled to the baryons. Otherwise, they would not be enhancing the height of the third peak. It's the same kind of lesson. The third peak, in a more indirect way, tells you the same thing the bullet cluster does. There's a source of gravity somewhere where the ordinary matter is not.
I misunderstood the third peak argument. I thought it was you were allowing some modification of gravity plus some form of dark matter when it didn't fit.
Right. Well, there's a specific modification of gravity that it didn't fit. The thing that I like better about the bullet cluster is it doesn't care which modification of gravity you have, so long as the gravity is still being sourced by the ordinary matter. Okay? So I think that an argument from the third peak works just as well, but it's more indirect. Do you know what I mean? I mean, as a personal note, this was what stopped me from thinking about modifying gravity to get rid of dark matter, the third peak. I stopped thinking about it then.
But if we took Tevis plus neutrinos plus lambda,
Yeah?
right? Is there some combination that would fit all the data?
No, this is Tevis plus...
So Tevis is ruled out.
Yeah.
Right.
Tevis is ruled out, and this rules out even post-Tevis, without enough dark matter to explain that. Yeah. Okay. So, where are we? Where do we end up? It is still true that MOND fits the galaxies. You know, that remains a fact about the universe, which is worth trying to understand within the context of theories that have dark matter in them. The failure to fit clusters in the CMB makes it difficult to believe, makes it very difficult to believe that modified gravity is the sole explanation for rotation curves and for clusters of galaxies. The good thing about, Bekenstein, his timing, not so good, because he invented MOND, finally made a relativistic version, just as the data became good enough to rule it out. If he had done that like in 1990, he would have had a whole industry proving him, testing him, and before finally ruling him out. The cosmology of MOND is better than you expected, which is a cautionary tale, but the third peak is a problem. The bullet cluster is really saying, again, that if someone asks you, what does a bullet cluster prove, the answer is dark matter exists. That's not the same statement as MOND is wrong, or Tevis is wrong, or anything like that, or gravity is not modified, but dark matter exists, which is pretty good. Thank you. Yes?
So there's another argument I've heard for dark matter, which is like the time for structure to grow. So the initial perturbations we know are like 10 to the minus 5.
That's right.
But they decoupled only at sort of z of 1,000 1,000, and so there wasn't time for them to grow to order 1. What would ordinary matter? So that turns me dark matter started collapsing.
That's right. Yes.
So
yeah.
Did modified gravity have a chance of sort of
yes.
solving that?
Yeah, because that argument obviously only works. I mean, not only works, but certainly relies on the equations that the perturbations satisfy, which include general relativity. And this is good evidence that mon plus lambda plus neutrinos solves that problem. Tevis, this is really Tevis plus lambda neutrinos. It does an awfully good job.
But with neutrinos.
With neutrinos, yes, that's right. Without the neutrinos is here, it's not so bad, but it's still not great. Anything else?
The motions of satellite galaxies around
Well, what you want is two different ways to probe the gravitational potential. In fact, what you really want, as a general rule, to test general relativity in cosmology is you want to probe phi and psi separately. You want to probe the perturbation to the time-time component of the metric and the space-space components, and then compare, because you can sort of separately get from that reconstructions of the gravitational potential in the Newtonian sense, which is predicted uniquely by general relativity, see if it is fitting the data. Just looking at any one test of the gravitational potential tells you nothing, because you can put stuff in there. You could either modify gravity or put dark matter in there. You really need sort of two complementary things.
So only one other question. Why was Einstein right?
Why was Einstein right? Here's why Einstein was right. Because that's a good question. What did Einstein do? Einstein imagined that this guy was the only massless degree of freedom, and that couples universally. In fact, the real question is, what would life be like at the Planck scale, where we could measure all the massive modes of the theory of everything? And life might be very different. We live in a universe where we only have access to the modes of vibration of the fundamental universe, which are very, very, very light compared to all the relevant scales of particle physics. So the real question is, why do any fields remain massless? It's much easier for fields to get big masses. And really, the only reason why fields ever remain massless is there's some symmetry protecting their mass. So the reason why Einstein was right is he found a mode which was protected in its mass by a symmetry, which is gauge invariance of coordinate transformations. He didn't think of it that way, but that's why he was right. No. But that's why he had a chance of being right. I mean, why didn't Bronston-Dickey get it right? Because it's easy to give a scalar field of mass. It's hard to give a spin 2 field of mass.
Can we go back to the bullet cluster?
Yeah.
I think there's a danger overstating the case. And the danger is that you gave a long story about the past history and the interpretation of where the stuff is and what it is. You don't know all that. You have a plausible story. You see some stuff. People try to think, gee, what could cause this? And, there's a pretty good story for that. But you don't know that that's the whole story. You don't know that there wasn't some funny mixing of the dark matter and so on.
Oh, you mean for the past history of the cluster?
Yeah, and you're using that. You're using that to say, well, that's why the hot gas is here, not there. You've got a whole kind of
that's true.
History, biography.
Yes.
Astronomy, I call it.
Archaeology, yes.
Which, you wouldn't want to use in too sharp a way to cut against these theoretical notions, that's all. So
that's fine.
I think you
that's fine.
Not to overstate the case.
I'm a big believer in never overstating cases.
Now, wait a minute. Say that again. More definitively. More confidently.
I was trained as a graduate student to always state the case exactly as well as it should be stated. So, but I think this is a good case where. Here's what I think the case is. This is overstating the case. This blue thing called dark matter. Well, it's not my picture. I took it from a screenshot. But the blue thing is gravity. This is where the gravity is, reconstructed from lensing.
My theory is
the red thing is where the
galaxies got more massive as a result of this collision.
I've already written down that theory. It doesn't work. I think I'm pretty I'm pretty, I think it's okay to say that's where the ordinary matter is. I think that's okay.
I'm not disagreeing with you.
No, I understand.
This is a particular event that took
You
place
would love to see more than one.
circumstances.
You would love to see more, yes. Actually, I think, but
The world is full of illusions.
just like no one believed the universe was accelerating until it was attacked by some different phenomenon.
No, it's just proven by better supernova.
I think that this is the thing that convinced me that the gravity is pointing somewhere where the matter is not, where the ordinary matter is not. But it's a little bit I know, exactly. I almost didn't believe myself.
I like the other thing was a picture.
But that's right. Exactly right. This is, even though I think that the correct interpretation to put on this is that I'm seeing the influence of gravity where the ordinary matter is not, it's a long road to get there. Whereas in this picture, I see, ooh, look, there's the ordinary matter, there's the gravity. They're not in the same place. But I think, but the reason why I'm saying that is because I think that this is a confirmation rather than a first demonstration.
Right. You have a story for what you think the dark matter would do, and you think you know what hydrogen atoms do, and they bump
Hydrogen
into each
atoms,
other.
yes.
Sure enough, this looks like that.
Yeah.
But also the lensing map is a bit different if you would put all your mass in the galaxies.
Oh, yeah.
The lensing mass would look different than it looks.
I mean, the place where there's a lot of astrophysics, right, is getting a mass out of that extra surface rings.
Absolutely. That's a lot of astrophysics. So if you really didn't believe in dark matter, and you wanted to invent a theory of gravity that would fit all the data, you need gravity that is responding. I was not joking. You need gravity which is responding to where the matter would have been if the history of the movement of matter had been very different. I can't prove you can't invent such a theory. You know, your least favorite graduate student could be assigned that as a project, but I'm not going to work on it. Which is my own little standard. I hope my least favorite graduate student's not listening to this on the web. Any other questions? I love all of my graduate students.